This is problem number 26. It is definitely some calculus. You're taking the limits of this expression, and basically, let's well, I'm gonna start with this. I'm trying to figure out how best to explain this, given the fact that you haven't had calculus week for those of you taking the GACE class in the summer of 2018. So, a limit. Very quickly, most of the time, like with a polynomial, if you have the limit as x approaches 2 of x squared plus 4x, essentially what that means usually is, what is the y value at 2? And so a lot of the time, it's just plugging in. So 2 quantity squared plus 4 times 2 would give you 4 plus 8, which is 12. So the limit as x approaches 2 of x squared plus 4x is 12. Okay? So direct substitution of the limit is awesome. Unfortunately, that's usually not what happens on some of these questions, especially when it's limit questions. And let me show you why that is. If you tried to plug 0 in for theta, okay? So you would end up with the tangent of 2 times 0 over 3 times 0 times the cosine of 4 times 0. So it is essentially the tangent of 0, whatever the tangent value is at 0, over 0 times the cosine of 0, which means the denominator will be 0. And if you think about the unit circle, this point right here is 1, 0. So at 0, the tangent is y over x, so 0 over 1. All right, you get 0 over 0, which is not a number. It's undefined because of the bottom, and 0 over 0 is indeterminate. Now, I will tell you there is something called L'Hôpital's rule. L'Hôpital's rule, it's a guy whose last name is the hospital in French, but L'Hôpital's rule basically says that when you get a 0 over 0 indeterminate form like this, you can take the derivative. If any of you remember your calculus right now, you'll remember that taking the derivative means essentially finding f prime of x. Okay, you can take the derivative of the top and then separately take the derivative of the bottom, so numerator and denominator, and then see if you can evaluate the limit at those places. And that is how you can determine the limit. And you can do the first derivative or the second derivative, whatever it takes to get you to a point where you can actually do direct substitution in indeterminate forms. And I should be clear when I say that. You can take the derivative as long as it keeps being indeterminate. Okay, so let's look at, I'm going to do the derivatives, and I will accept that you probably can just turn it off or fast forward, but here we go. If I've got the limit as theta approaches, you know what I'm going to do? I'm going to change that to x because I don't like using a theta and a 0. I can see theoretically that could make a lot of issues. Of the tangent of 2x over 3x times the cosine of 4x. Okay, so the derivative of the top, I want you to notice that 2x is a function within a function. So equals the limit as x approaches 0 of, I do the derivative of the outside. The derivative of the tangent is the secant squared of whatever is in there. But then I've got to dig in and get the implanted equation and find the derivative of that. The derivative of 2x is 2 over, and I should do this just to be clear, over, now this is a quotient of two functions. And so you have to do the first function times the derivative of the second. Now, the derivative of the cosine of 4x is negative sine of 4x. Again, another implanted function, because 4x it by itself is a function as well. So times the derivative of that, which is 4. All right, so continue with the product rule. First times the derivative of the second plus the second times the derivative of the first. And the derivative of the first one, 3x, is 3. All right. So now what I'm going to try to do is simplify this and then evaluate it at 0. So I will tell you that calculus professors get really upset if you just go equals and start doing your math, because the limit of something is not equal to that something. Okay, so you should write the limit as x approaches 0 of, I'm going to pull the 2 up in front, times the secant squared of 2x divided by, and now I'm going to simplify this. I've got a 3x, a negative, and a 4, so that's going to be a grand total of negative 12x times the sine of 4x. Plus, again, I'm going to pull that constant 3 in front because I like it sitting there better. 3 times the cosine of 4x. All right. So now I'm going to remember back to, because basically what I'm going to do here is go ahead. Now, since I'm going to plug 0 in, I can ditch the limit, because when I put 0 in, that is hopefully the limit. So 2 secant squared of 2 times 0 over negative 12. You can see that when you add that 0 in, you actually are creating some really nice poof moments where entire functions go away because you're multiplying them by 0. Okay, so secant squared of 2 times 0 is equal to the secant squared of 0, which is equal to the secant squared of, secant is 1 over the cosine. So 2 times 1 over the cosine of 0, quantity squared. That's the numerator. Now the denominator, I want you to notice that when you take a 0 right there and multiply all of that, this entire highlighted thing becomes 0. So that is 0 plus, now I've got 3 times the cosine of 0. Okay. All I need to know here right now then is, what is the cosine at 0? So if you think about the unit circle, at 0, the cosine is the x value, so that's 1, 0. The cosine of 0 is 1. So that means that this entire expression is equal to 2 times 1 over 1 squared, which is just 2, over, and again, the cosine of 0 is 1. 3 times 1, which is 3. So the derivative is the limit is 2/3. Now, that was the full-on calculus version, which I hope that your hair didn't blow back too much. But stay tuned. I'm going to show you how you can get super, super close to a limit, any limit, without having to do derivatives, without having to do a lot of other things, because a limit means this. Sometimes functions, let me just put this in and show you what this function looks like. This function is, and this is not a function that you should know how to graph it on your own. Definitely not. Okay, so open the numerator. Tangent, open the tangent. 2x, remember the x is what you have to put there for this. And then close the numerator. I'm going to divide by, open the denominator, 3x. Now I'm going to make a mistake on purpose because I want you to see this. Cosine of 4x, close the cosine, close the denominator. When I hit OK, it's going to go, hey, what? And that is because when you are spelling out a word like cosine, it understands that as the cosine unless there are other letters, in this case x, sitting beside it. And then it does not understand that that's the cosine. It thinks it's a C, an X, a C, a 0, or not a 0, an O, and an S. It thinks it's 4 variables sitting beside each other, and it doesn't understand. All you have to do to fix that is put times, okay? 3x times the cosine of 4x. And then okay, and it's perfectly happy with it. If you look at the graph, it's kind of insane. If you zoom in, and we're zooming in on 0, what's going on right here? Hold on, I don't mean to do that. Previous, I'm going to do a zoom box. And I'm going to zoom in at on x equals 0, and I don't know where this is happening. somewhere around there. And the thing is, and you can't see this, there is a hole at 0. And let me show you where you would see it. You would see the hole at 0 if you go and look at the table. At 0, it says type unknown. So, at 0, it doesn't exist. But as you get closer and closer and closer to 0, it does exist. You might, kind of, if you do, go back to the graph, and if you do analysis, you could trace and evaluate and get like super close right there. Can you see that even though I'm not on it, it's 0.666 repeating? Or not repeating, but it's starting to repeat. And I'm thinking as I get maybe closer and closer and closer, so if I change that 2 to a 1 and then check, it's got 4 repeating decimals. If I change that 1 to a 0 there on the X so that it's an even smaller number, closer and closer and closer to 0, now I've got 1, 2, 3, 4, 5 repeating 6s. If I change that 5 to a 0, oh, look how many repeating 6s you get. So trace can get you really, really close. I know that 66666 repeating is the fraction 2/3. So I could actually guess 2/3 and probably come really, really close to getting it right. So you could either do it that way or you could do it with the table. And here's how you would do it with the table. Get some value and see how tiny, tiny, tiny that value is. It's not 0, but it's super close to it. And then I can tell it to make the little steps tiny. Okay. Did I do it? Nope. All right. Maybe it didn't like how many zeros. And can you see as you get closer and closer and closer? In fact, let's go on the other side of 0 also and look at that. It still didn't like it. Let's try it again. Okay, and I'm going to make this tiny, tiny little incremental steps. Okay, and so I'm starting at the negative, and as you go up, you will start to see that even though, let me get rid of a couple, at least 1 or 2 of these zeros. Okay, even though way back here as it gets closer, even though it's not exact, you can see the same thing. And that is that from here, from the negative side, it's 0.66666. From the positive side, it's 0.66666. As long as from both sides of the number, in this case 0, that you're taking the, causing the limit to approach, as long as they're approaching the same number, then a limit exists even if the function doesn't at that number. So 0.666 repeating is 2/3. So that is another way that you could get at a limit even if you don't know calculus-wise how to calculate that limit. And that is tiny increments, close to the number that won't work with direct substitution.